Okay. Okay, what we will do before I start, like the mean value theorem, because before I introduce this, I will introduce a little bit different form of the mean value theorem, and we call ROLLE'S theorem. Of course, it's based on the name of the mathematician, okay? The ROLLE'S theorem. Let's see what this theorem is telling me, and let's get like the intuitive understanding, okay, of this. One thing. Okay. Okay, that means what we have. We have to have a function, okay, that satisfies all of the three hypotheses. That means function must be a continuous function on the closed interval. That means we don't want to have any discontinuity, any holes, any jumps, any asymptotes. The hypothesis number 2, function must be differentiable on the open interval, since derivative is not defined at the endpoints. Okay? Differentiable means like a nice and smooth curve, no sharp corners, no vertical asymptotes, I mean vertical tangents, and of course, no discontinuity, but that was the point 1. And then having a value at the endpoints, f of a and f of b, the values have to be the same. Now it's the theorem. If we're satisfying this condition, there is a number c, yes, we can even see there exists a number c in that interval such that derivative at c is 0. Okay, yeah, probably simple, but as I said, quite powerful information. That's what this is telling me. How can I define graphically or geometrically derivative? What geometrically this means for you? F prime at c. Who can tell me that? My first question today. Yes, soon, 2 minutes after the session starts. It's the slope of the tangent, Alan. Thank you. That means slope of tangent. Okay, tangent, of course, tangent is the tangent line, but slope of the tangent at the point C. At C. And what kind of, what position will the tangent line have if the slope is 0? Yeah, what kind of lines has the slope? Horizontal. That means this means that the line is horizontal. Normally, if I have 2 points and I would like to compute, okay, actually I can get to that point later, because I wanted to give you the slope just of the line, but we're still talking about the tangent line. Okay, that means slope of the tangent line at some point C will be horizontal. Of course, if function satisfies all of the 3 conditions. Okay, and let's see a few few graphs. Okay, I have 1, 2, 3, and 4. So we can see the first one is actually just the line. Right? That means and the values of A and B are at the same level. They are the same. Yeah, that means all of the values, they have to be the same. F of A, the same like F of B. Okay, that means theoretically, every single number in that interval from A to B will have a slope 0. Tangent line will be 0. Slope will be 0. That means in this case. In this one, we do have the same values for A and B, and we can definitely see that at least 1 point exists in AB with the horizontal tangent. For number 3, we do have actually 2 points like that. Okay? And for number 4 is almost the same like number 2, but the other way, like the concavity is different. Okay? As we can see, that means this theorem is just telling me that that number C exists. Of course, with this condition. Derivative at C is 0, or the slope of the tangent at C is 0, the line is horizontal, tangent line. Okay? That means you may probably notice this theorem is not really telling me how to compute this. Of course, we know how to get the derivative and so on if the formula is provided. But this is just telling me that these values exist. And sometimes depends on the project, depends on the model. Sometimes it's enough information. And as I said, it's a lot to know that that number exists. Okay. That's me. Let's look at the first function. Verify that the following function satisfies the three hypotheses of the Rolle's theorem on the interval from 0 to 9. And function is defined as a square root of x minus 1/3 x. Root function, linear function, the difference, subtraction of two continuous function, it's definitely continuous function, and especially on the domain from 0 to 9. Okay, that means it's definitely continuous function. It's differentiable because that's smooth function and that's linear function. It's definitely differentiable, even if we will compute the derivative. Oh, excuse me, I think I was sneezing. Okay, and then we can check if f of 0 equals to f at 9. I did say equals sign, but we can compute here. If I substitute 0, oh, of course it's 0. But what happened if I substitute 9? Square root of 9, 1/3 of 9. Do you think it's 0? 3 minus 3 is 0. Okay, that means this is correct. Okay, that means what I can say that definitely the number c in the interval from 0 to 9 exists, but of course, what is the condition? Derivative at c is 0. Okay, that's what you can see. And it's just enough to check these three hypotheses of the function. So you can see how it's as I said, probably we need more, we would like to find out more information, but this is definitely good, enough information to know that between 0 and 9, that number exists. But what we can do, since the function is not really complicated, let's actually solve this equation for c. Let's find out the number, okay? Derivative. Derivative of the square root of x is 1/2 square root of x. We know that. Derivative of 1/3 x, 1/3. And now this derivative must be 0. What we can do, we can solve like that. I was thinking to get maybe the common denominator, but we can add 1/3 to both sides and cross multiply. Cross multiplying, I will have 2 root x equals to 3, root x equals to 3/2. Now, to solve for x, I will square both sides. Squaring both sides, I will get 9/4. And 9/4 is like 2 1/4. It's definitely in my interval. Yeah, so we can see however the function looks like, I don't know exactly. I know that at 0 is 0, and let's say at 9 is also 0. It's not like parabola, but it's something like that. But actually my graph, because at 2 1/4, which is 9 1/4, we're supposed to have horizontal, my graph is horizontal tangent. Yeah, I just want to, okay, that means that's, derivative at c is 0, and that's my c value. Great. But one more time, the point of the theorem is just to prove that the number c exists. Okay? Not really computing, but we may ask you to compute this like I did. Yeah? Just simply follow the equation. Okay, now I do have a nice list of the function, and you would like to, I would like to ask you to tell me which function is applicable for the Rolle's theorem. Okay? Which means we're just checking continuity, and we're checking if the function is differentiable. and if the value at -8 and +8 is the same. Okay, let's take x squared. What do you think? Is function x squared good for the Rolle's theorem? I think it is, because it's nice and smooth. That means we can see nice and smooth. And what is the value at 8 and -8? I can draw a little bit. Is this value the same? Yes, thank you, it's 64, okay? That means function, it's continuous, differentiable, nice and smooth, and the value at 8 at -8 is the same, okay? This function is good. Definitely the value C exists. Actually, looking at the graph, not even computing, can you tell me what is the value C? The derivative is 0 at C? It's of course 0, because I can draw a horizontal tangent at 0. Yes? Okay, good. Okay, what about x cubed? Does x cubed is good for the Rolle's theorem? It's no, of course no, because, and can you tell me why it's not good? It's continuous function and differentiable function everywhere, but what happened if I cube -8 or if I cube +8? Yes, the values are not the same. Value for -8, it's not the same. They will be not the same. Yeah, that's always good to check that first. Okay, that means we will not apply the Rolle's theorem here. Okay, cube root of x. Probably I can say the same thing. The negative, right? Okay, yes, thank you. Thank you, Ramiro, Alan, Regina, Jake. Yes, everybody, it's participating really well. Cube root of -8 and cube root of +8 is not the same. Even if the function is, let me actually draw it for you, because cube root of x looks like this. And the one thing also, this will be the value for -8 and +8. But since this is function inverse to x cubed, we remember we do have horizontal, vertical tangent. Vertical tangent at 0, which means derivative at 0 is undefined. Function is not differentiable at 0, even if we will look at the formula, right? Because we can also find x to the power of 1/3 will be 1/3 x to the power to the -1/3, which derivative is cube root of x squared in the denominator. We remember from last week, a critical number will be 0, because it is in the domain, but it's the 0 of the denominator of the derivative. And that's the proof. Okay? That means at 0 function, it's not differentiable. That's when we have additional thing, the hypothesis is not, we're not satisfying the hypothesis, okay, of the function being differentiable. Okay, and number 4, x to the power of 2/3. Another function that we should know, it's a cube root of x squared. That means looks, it's almost like this one, like cube root of x, but everything what was negative below must be positive. That means this one will be a little bit higher. Okay, and we can see right away. Values will be the same for -8 and +8, because we're squaring the number, which I think will be, who can tell me the value for 8 or for -8? We have to take cube root and square. Cube root of 8 and square. Cube root of 8 is 2, and squaring that number, we will get 4. That means the values actually are the same, but function, it's not differentiable at 0. The same thing. Computing a derivative, we will get this. No? Okay, what about absolute value of x? Is this function differentiable everywhere? Absolute value of x. We do not have derivative at 0, because we do have a sharp corner. Absolute value of 8 and negative 8 is the same, but not, at 0 we do not have derivative. Okay? This one, now the function number 6, I can draw it for you. It's just the half of the circle with the radius 8. Okay, 8, 8, 8. Oh my. Let me just, 1 second, I will switch off a few things. Okay, now should be better. Can you, yeah, you can still hear me. Okay, that's, we can see number 6, actually I will not, it's just the half of the circle with the radius 8. Okay, that means the value for negative 8 and for 8 is the same, and we can see it's nice and smooth curve. Function is continuous and differentiable. This function will satisfy the conclusion of the Rolle's theorem. Do I have room? Oh, I do have room. Let me show you, because we have to know that function. Yeah, it's number 6, just one more time. Like, if you don't know what is the shape of this, we may try to rearrange this function a little bit. I will square the function both sides, and I will add x squared to both sides. Do you recognize this equation? Who recognizes this equation? Probably everyone. No? Yes, of course, it's the circle. That's me now. Okay, that's the circle. Negative 8, positive 8, and so on. With the, of course, the 64 is telling me the square of the radius. But now, if I will take this circle, this equation, and I will ask you, please solve this equation for y. What you will do? You will go to this step, you will subtract x squared, and then you will take the square root of both sides. But what you will have? We will have plus or minus. Yeah, we remember we always algebraically we have to take positive and negative. And now positive means the positive part of the circle, and negative means the negative. And since we only have positive in our original equation, that's the reason that is half the semicircle, the upper one, okay, positive, okay? That means just to deal with this formula. And then we do have the last one, absolute value of x squared minus 64. Also important, helpful to know how the graph looks like, because we can try to find out the derivative, but let's graph a function. Okay, that's what we will do. First of all, we will try to draw a function inside x squared minus 64. X squared is just the parabola, minus 64 means that I'm dropping 64 units down. And this will be, this will be 8, the distance 8, because when I square this, I have zeros. Okay, but this is still the function inside, okay? Now, taking the absolute value, what this means? If I have positive numbers inside, we know that absolute value of the positive number is just positive number. That means this will stay, that's positive. Above the x-axis is the positive values, right? Now, absolute value of negative numbers, they simply become positive. That means I have to do the reflection. Oh, a little bit. Okay, that means this is gone. This is a beautiful function, absolute value of that parabola. Okay? Everything what was below must be reflected above the x-axis. Okay, That means if I will take the interval from -8 to +8, okay, I think I do have a nice smooth function. If I will take a little bit wider interval, then I will have these corners. Then the function will be not differentiable. But just on the interval from -8 to 8, it's almost like the half of the circle. It's parabola, that means it's a little bit oval, different, but that means this function is also good. This one, and of course this x squared. Okay, that means just make sure that you know these functions, because then it's easy to answer some calculus question. Okay, let's keep working. We will skip this question, okay, because this one is kind of like a connection of the intermediate value theorem and the mean value theorem. Okay, that means don't worry, it's good for the practice. It's not really good on, like, yes, on the test. I do have a solution. Oh, you can see, you can pause the video and you can try to, probably it's understandable, like it's easy to follow, but let's just leave it. Oh yeah, ROLLE'S theorem. I think I did set the mean value theorem. Okay. What else? I do have some notes, but we can skip these notes for now, because I would like to introduce and show you the mean value theorem. Okay, that's what we will have. First of all, I can tell you that the mean value theorem, it's almost the same like the ROLLE'S theorem. But let's see what is the difference. Again, we need a function to be continuous function on the closed interval and differentiable on the open interval. Okay? Then there is a number c in the interval AB such that, and this is the relation, derivative of that c is actually not 0, like was for the ROLLE'S theorem, looks like this. And you probably recognize f of b minus f of a, b minus a. One thing that is different, the values at a and b, they don't have to be the same. Okay, no. Because let's look at this. When we have the same values, a, f of a, b. Okay, that we do have, and that's the ROLLE'S theorem. Then I can definitely find my point C with the horizontal tangent. If you will notice, connecting the endpoints A and B, what kind of line I am creating? Is this line, what is the relation to the blue line? If I will they are also horizontal, right? That means they are actually, we can call, like, more using general term, parallel. When I connect these, because they have the same values, that means they lie on the same level, it's horizontal line, the same like my blue line, because the slope was 0, derivative was 0. Okay, that's, we can see we did create parallel lines. Slope of the tangent line is exactly the same like the slope of the secant line, because the green line I can call secant. Okay, I can write secant and tangent. And now, what we have for the mean value theorem, we have almost the same condition. The only thing that is different, f of a and f of b, they don't have to be the same. That means, let's see. I can draw maybe the situation like that. F of a, and let's be a little bit higher. Okay, and what is now the theorem telling me? Because I still have continuous and differentiable function. The theorem is telling me that f prime at c, which is still the slope of the tangent line, must be exactly the same like f of b minus f of a, b minus a. What do you think? What is this right-hand side? F of b minus f of a, b minus a. Do you think it's the slope of the secant line, the average rate of change? If I will connect this, yeah, it's simply the secant line, because how can I get the slope of this? I will get the changes in y over changes in x. That's the slope. And now the theorem is telling me that at least one point, they should be horizontal. Now it's not really zero, right? But they are the same. The same means graphically they are parallel lines. Okay? Not horizontal. They are just parallel. That means slope of the tangent line at some point C is exactly the same like a slope of the secant line connecting the endpoints at the endpoints. That's that's the mean value theorem. It's more like general. It's the same idea, but the value could be different values for A and for B. We can see the connection. For ROLLE'S theorem, we have horizontal, we have 0. For the mean value theorem, it's just this. Okay, that's pretty much the mean value theorem. And again, this theorem is just proving that this number C exists. Sometimes the function is too complicated that we will be not even able to compute that value C, okay? But sometimes it's easy to compute, but this is just proof that this number exists. And again, looking at this box, the equation, it's a really nice connection between the derivative and the function. Yeah, that's what I said at the beginning, that it's good connection. We can get some information just from the values of the function. We can get some information about the derivative, okay? Even pretending that we don't have the formulas, just the exact values. Okay, a few notes. Oh, okay, that's what I was trying to draw it. Okay, we can see the point C exists, okay? But this means that the tangent at the point C has exactly the same slope like a secant line. Okay? Slope of the tangent line is the same like a slope of the secant. That slope of the tangent, that slope of the secant. The same means the lines are parallel. Okay, nice interpretation. And what else I have? Yeah, just the like a application, because of course the rate of change, it could be the distance over the time, which is the velocity. This means the instantaneous rate of change, instantaneous velocity, and that's average velocity. That we can, for example, we may have this application. For instance, if a car traveled 180 kilometers in 2 hours, it's easy to compute the average speed, average velocity, just 180 over 2, 90 kilometers per hour. But what also this means that the speedometer must have read this value, 90 kilometers per hour, at least once. Because we remember, like, even if my average speed is like, I don't know, 50, 60, 70, doesn't mean that I was driving all the time that values like 50, 60, 70. Okay? But if based on the mean value theorem is telling me that at least once I was driving exactly 90. I could drive like 91, 92, maybe 87, 85, okay? But at least once I was definitely exact 90. Yeah, that we can see that's at least one, like that's the instantaneous of comparing to the average. Okay. And now let's do a few examples and we will be done for today, because it's only that theorem today. Example number 3. Use this graph to estimate the value of C, okay, that satisfies the conclusion of the mean value theorem from 0 to 8. Actually, I can keep the blue. Okay, that's what we have. We do have a function defined from 0. Oh, I'm trying to make more clear. From 0, 5, 6, 7, 8. Okay. I mean, what I can do, maybe I can use. I know that the mean value theorem is telling me that the slope of the secant, okay, which is, oh, do you think you can compute the slope of the secant, the green line, for me? Rise over run. 1/2. It's 1, 2, 3, and 8. Yes, that will be more. I can actually use the same color. I mean, we don't really have to know exactly, but yeah, just here, 3 over 8. Okay, and now we know, because function is nice and smooth, continuous, differentiable, that at least one number, oh, that's supposed to be C, that at least one number C exists, which derivative at C is exactly the same. And this is tangent, slope of the tangent. Slope of tangent. Okay, that's what I have to do. I have to just draw a blue line, which will be a tangent, and it will be parallel to the green one. Do you think you can tell me the x value? Like, where shall I draw? I don't know if my drawing, I'm guessing maybe, a little bit too, a little bit lower. Okay, let's pretend that that's tangent, should be a little bit lower. Yeah, that means somewhere here, yes, like do you think this could be the C value, like 2.8? Okay, yeah. Yes. Jake said 3.5. 3.5 will be actually horizontal. Okay, that's different. Yeah, 3.5 and 6 will give me horizontal line. I don't need the horizontal line because my values at 0 and at 8 are not the same. Yes, I'm looking at the line that it's parallel to the secant. Yeah, they have to be the same. That means that will be good, Jake, for the ROLLE'S theorem, of course, making f of 0 and f of 8 equal to. Okay, can you give me, I think we have one more value of C. Where shall I draw the line that will be also, yeah, like C, yes, Regina, 6 point, like a little bit, I can draw it. Oh, okay, I think I like 6 point, that means that's another value, 6.2. Oh, 6.2, do you remember? I started the session saying that this is section 6.2, which is actually 3.2. Yeah, weird. Okay, 6.2 and 2.8. Okay, that's actually it. That's how we can, that's the question that is actually testing if you understand the theorem. Okay, let's see. Alan is asking, oh yeah, I'm kind of like, yeah, of course, I'm kind of like guessing. Could be 6.2, 6.1, 6.3. Of course, it's not 6 and it's not 7. Yeah, we can definitely see that 7 will be too steep. I mean, when you accidentally said 6.2, oh, no. I see. No, I had no idea. It's just the really coincidence. Of course, nice coincidence, numbers. As I said, we always like connected. I also teach Math 141. I was teaching actually in the morning, and we have more like theory numbers, like sequences, and I was saying something about connection. We all connected through the numbers, shapes, patterns. Okay, that's, yeah, if you will take Math 141, you will have nice class with me. But okay, no, I didn't even think about this. No, not at all. Yes, but yeah, we all connected. Okay, let's solve a few more problems. Okay, example number 4. Verify that the following function satisfies the 3 hypotheses, which actually should be 2, because 3 is for the ROLLE'S theorem, of the mean value theorem, and function is defined as a x cubed minus x from 0 to 2. From 0 to 2. Okay, that means that's just a polynomial. Polynomials are always continuous function and like nice and smooth. Derivative exists, differentiable. Okay, that means if this function is continuous and differentiable, I can definitely say, okay, that the value C exists. Did I type this? I did type. The value C exists, the derivative at C is equal to the slope of the secant line between 0 and 2, which this is the equation, f of 2 minus f of 0, 2 minus 0. Okay, that means I will definitely have a tangent line with the same slope in that interval. And we can actually try to compute what's the value at 0. 0 cubed minus 0, that's actually funny. Can you tell me the value at 2? 2 cubed minus 2. 6, please check. Yes, thank you. Good, thank you. Because the arithmetic, you know, sometimes it's crazy. Okay, did I type this? Yeah, I did type. That means let's see what I did. This is just a theorem, and we definitely satisfying, but I'm trying to compute that value C. Yeah, let's just check. This is the derivative, okay, because having a function x cubed minus x, I will have 3x squared minus 1. I just keep C for x, but that's, yeah, the same thing. And then 6 minus 0, 2 minus 0. 6 over 2 is 3. Adding 1 to both sides is 4. Dividing by 3, oh, I did solve a little bit faster. I did divide both sides by 3, and now I took the square root of both sides. Square root of 4 is 2, square root of 3 will stay square root of 3, and plus or minus. Okay, but the thing is, only positive number is in my interval. That means probably this function also has another point, that the tangent will have a slope. What is my slope? That's actually the slope, right? This is the slope. Because the other steps are like just my solution. Slope of secant. Okay, and this is of course slope of tangent. Slope of tangent. Yeah, they have to be the same. That means it is 3. Slope of secant. That means at this point, 2 over square root of 3, I know it's a weird number, but it's definitely positive, greater than 0 and less than 2. At this number, the slope of the tangent is exactly like a slope of the secant. And I think I have a graph for you. Oh, and we can see that means this is 2 over square root of 3. That's the function. This is 0 and 6. Yeah, because it's 3. Okay, that's the values. Blue line is a secant line, pink line, it's the tangent line. And you can probably see here, negative 2 over square root of 3, kind of. Yeah, I will draw the same, but it's outside my interval. Yeah, it's just different interval. I will draw the same tangent. I mean, with the same slope. Okay. Oh, another question, and this is like a typical question that you could be asked. We may ask. I can ask you. Find a number C that satisfies the conclusion of the mean value theorem for the given function on the given interval. And function is 9x squared plus 5x plus 6. Parabola, nice and smooth function. That means it's definitely continuous and definitely differentiable. Okay? Oh, I didn't type. That means I can say right away that the derivative is the same like a slope of the secant line. Okay? And derivative, I can compute the derivative, 18. Let's put C. 18C plus 5. And I can put the values f of 5 minus f of negative 5. 5 minus negative 5. A and B are 5 -5 and 5 respectively. And 18c plus 5. Do you know where the 18c plus 5 come from? Everybody is, because I don't want to jump too fast. Yeah, derivative, thank you. 18x plus 5, but I use the c. Now I need your help. Let's divide. You have to take a function and substitute 5 and -5. Oh, who can help me with this? 5. 9 times 5 squared plus 5 times 5 plus 6. And -5. Oh, okay, 256. Because this one is almost 250, because if this will be 10 times will be 250. 225 plus 25, which is 250. Yes, thank you for helping me. And now let's find the value at -5. -5 squared is the same. Oh, you fast. This will be minus. That means it's 225 minus 25, 206. Very good. Okay, that means I have 256 minus 206, 5 plus 5, 10. Oh, 50 over 10. 5. Oh, actually 5 and 5. 18c is 0. C is just 0. Okay, that means at 0 we will have that tangent with the slope. Let me just say this is the slope, right? Because that's the slope of secant and slope of tangent. The slope of tangent. Okay, I don't know exactly how this parabola looks like, but I can just, yeah, because I need probably some zeros, but we know that at 0, the slope will be 5. And, oh, we know the values are really big. Okay, let's try, I don't know if that's good. Oh, no, it's positive. Am I actually the other way? The value at 5 is 256, and value at -5 is, of course, my scale is terrible, but I'm just trying to give you the idea. Slope of the secant, okay, 5, and green, slope of the tangent. Oh. I really wanted to be parallel, but at 0, yeah, C is 0. Something like, yeah, something like this. Parabola and connecting endpoints will give me the same slope. Okay, but we can see this, the middle part is, that's what I would like you to do. I mean, all of the additional things, I'm trying always to give you some more explanation, but that's the equation, and that's what we will ask. Okay, let's see, I have 2 more problems, I believe, because we have, oh yeah, that's another thing. Suppose that f of 0 equals to -3 and f prime of x is less than or equal to 5 for all of the values of x. Okay, how large can f of 2 possibly be? Okay. Of course, asking this question just this way could be probably challenge. If you will see a question like that, I might give you a hint that please use the mean value theorem, okay? Because what we see, we have the value at 0, okay? We have the value at 0, and they asking for the value at 2. That means I'm assuming that I have some situation between 0 and 2. Okay, and then I have some information about the derivative. Okay, that means this is the connection between a function and derivative. Okay? That's the reason that I will think that the mean value theorem is a good is a good tool. Another thing, because for the mean value theorem, I need a function to be continuous and differentiable. But having this information, yeah, derivative is less than or equal to 5 for all of the values of x, which means derivative exists. If derivative exists, function is definitely continuous. Okay, that means I think I type this information. And what I did, because I typed my answer like using the equation, but I would like to show you the graph, and you will actually give me the answer. Actually, do you know the answer? How large can f of 2 possibly be? No? Okay, you will give me in 1 minute. Let's see this. F of 0 is -3. Okay, 1, 2, 3. Actually, no, I need 2. Okay, let's say this is 2, because I want wider. Now, that means I have the situation at 0, and they asking me, how big is f of 2? That means f of 2, I don't know, it's here, 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 I don't know. Yeah, somewhere, the f of 2, I don't know the values. But I also know that f prime derivative is less than equal to 5, which means slope of the tangent line, okay, slope of the tangent is less or equal to 5, right? That means I can maybe draw 5. 5 is like, maybe like this. Okay? That means I know that slope of this line, slope is 5. That means, do you think you can figure out that value? Because this will be f of 2, if this is 2. Let's look at this. Okay, slope is simply a rise over run. What is the run? What's the distance between 0 and 2? Between 0 and 2 is 2. Now, if the slope, yeah, must be 5 or less, of course, because I could draw a rise over run must be 5. That means what value I have to divide by 2 to get 5? What value? It's 10, okay. That means the entire distance must be 10. And look at this, I've already have 3 units. That means what is this value? What I need? I need 7, yes, that's what I wanted you to answer. Oh, that's 7. Really good. Okay, that's what I wanted. That means this is, of course, could be lower because I picked the highest value of the slope. The slope could be lower than 5. Okay, but we can, and this is just, yeah, just like the average rate of change, instantaneous rate of change. Yeah, it's simply the mean value theorem. But we can see based on the slope, we just know that this must be 7 because the whole rise must be 10. Okay. But let's look at like the maybe more formal. That's the mean value theorem. Everybody knows this. And then f of 2, we don't know. F of 0 is -3. And 2 minus 0, of course, is 2. And the maximum, you can see I did pick the maximum value of the derivative, 5. Okay, that means this means that I'm computing the largest possible value of f of 2. I can multiply 2 by 5, 10, and I can subtract 3. That means this is more like formal, but sometimes I'm worried that maybe we will not understand, but we can see what that's the situation. That's what's going on. Okay? But I'm happy that you put the answer 7. Okay, I have one more like that and we will be done. This means that you understand this theorem. Yes, the largest possible value of f of 2 is 7. Okay, let's do this one. It's actually similar. Yeah, it's similar. It's the other way. F of 1 is 15. F prime of x is actually greater than or equal to 6 for all of the numbers between 1 and 7. Okay, That's fine. That means we're looking at the interval between 1 and 7. And how small can f of 7 be? Also, I have this, but I would like to draw the situation. And you will answer the question. What values we have? Okay, I will draw like that. X and Y. 1. At 1 is actually 15. No, because the slope is, let me do a little bit weird scale. Okay, I just don't want to run out, like outside my slide. And 7, we don't know. Yeah, 7 could be any of my dots. And what I know, what 6 means? Can you tell me? Do you remember from the last question? F prime of x. What is the explanation, geometrical explanation of f prime? It's the slope of the tangent, yeah? A slope of the line for us at the moment. That means 6. Okay, let's say this is 6. Slope is 6, and we're looking for this. Could be greater, right? You see, f prime could be greater than 6. That means I can draw a little bit more steep, but let's see just this. Okay, the same situation. Slope 6, that means rise over run. Okay, this is rise, this is run. How many units we have between 1 and 7? Okay, actually 6, okay. That means now, what number I have to divide by 6 to get 6? What number I have to divide by 6 to get 6? 36, okay. That means this distance must be 36. If we are already 15 units up, what will be that height? What do you think? I think we have to just subtract these numbers, because we have 50, it's 21. 21 plus 15, oh no, hang on. No, oh no, don't listen your instructor. I think, no, I think I said that we have to, no. Who can help us? Yes, I think because between 15 and 21, we only have 7. We actually have to add them together. I think it's my fault. I don't know, for some reason I thought, no, we have 15, but we have to have 36 units. Yes, it will be 41. Okay, yes, everybody agree? Yeah, we can subtract, because 41 minus 15 will give me 36. 36 over 6 is 6. Okay, that means this is the smallest possible value, because we may have higher. Okay, that means we can see how nicely we can combine the information about the function and the information about the derivative. Yes, 50. Oh, thank you, Colin. Did I say 51 and type 41? Thank you. And actually, yes, Regina also said 50. Yes, 15 plus 36, 51. Okay, and I also typed for you the nice systematic way. Okay, that's the smallest possible value of the slope, f of 7, f of 1, and the difference. 6 times 6, 36, and adding 15 is 51.